Hey everyone, today we'll find area bounded by polar curves. First, we'll tackle the idea behind the concept. The concept builds on sector area. Let's imagine a theta degree slice. From geometry, how do we find area of a sector, area of a slice? Theta over 360 times pi r squared. But in calculus, we always use radian. So we can't find the area of one slice. If theta is in radian, we can't divide it by 360. We have to divide it by 2 pi. So this will be theta over 2 pi times pi r squared. Pi's will cancel. So area of a slice will be 1/2 r squared theta, where theta is in radian. In the first formula, theta over 360, theta is in degrees. This is not as well known as the first formula. All right, how this will help us to find area bounded by polar curve. Let's find region R. Region R is bounded by f of theta. Well, they give you two functions. How do we know which one is for which curve? We can quickly plug in 0 for theta over here and realize 2 times cosine of 0 gives you 2. So when the angle is 0, it's supposed to be at 2. So g theta models this curve. So as theta is 30, as theta is 45, as theta is 60, the distance from the origin is modeled by g theta. So how far is the radius, how far is the r based on theta value for the semicircle? This is g theta function. For the bean-shaped like function, I think it is f of theta, right? And so as the theta values increase, it's like you're walking around the curve. And when theta is 0, we're here. When theta is 45, we're here. When theta is 60, we're here. You can calculate these r values to examine the curve. When theta is 90, r is back 0. So let's draw infinitely many, infinitely small sector slices. Please imagine these please imagine these as infinitely small slices. So we can't draw infinitely many of them, but imagine what if we were able to draw infinitely many of them. They're all originated at the origin. And the last one will be at 90 and it will be 0. Remember, integral concept is always about adding infinitely many, infinitely small things to each other. How can we find the area of this infinitely small slice? Let's say we zoomed in. The d theta is right here, and this is r. The area of this infinitely small, infinitely thin slice is 1/2 r squared d theta. We have infinitely many of them. We use integral to add infinitely many, infinitely small. That's the meaning of integral. So theta values will vary from 0 until 90. We can put 1/2 outside or inside and r squared d theta. In order to write this response on the AP exam, we should always begin with labeling. I can kick 1/2 outside, as I mentioned earlier. This was our thinking and building the concept over here. Now we're putting the answer together. So it's 0 to 90. Instead of r, as you know, which curve are we walking around here? The curve we are walking around here is f of theta. So we could copy the whole function, or we could just write f of theta. So since the question already labeled it as f of theta, I'm just going to refer to it as f of theta. 1/2 r squared d theta. We're adding these infinitely many, infinitely small slices. This integral is 1 point according to the rubric I checked. And the final answer is 0.684. That is also 1 point. Students, after typing this using Math 9 carefully, should either truncate the final answer, which means just cut it without rounding, or round it to 3 places correctly. The answer is 0.684, and we just scored 2 out of 2 points. Thank you for listening. Don't forget to subscribe to my YouTube channel.